Okay, why don't we get started? So we have only one more class after today, which is on Wednesday, and then there's a final exam, as all of you know, on Friday, and then we'll be done. So as I mentioned in one of the Piazza posts, there is no homework 4. I removed the homework from the schedule because it was quite tight, and then we have exam this week, so I just decided not to have it at all. Okay. The other announcement I do want to make is you should have received a request for course evaluations, right? The response rate is 3%, which means maybe 2 students have replied so far. Okay. Well, okay, the 3% is all here. So I would appreciate it if you actually go in and provide feedback, because it's important to know your perspective of what the course looked like, and especially when you put comments, I do get them and read them carefully and make adjustments for future years. So I'd appreciate taking the time and actually entering your evaluation. Okay. Usually we used to do that in class, but now they have made it Inspire, so it depends on you responding, finding time to respond. Okay, so let's get started with your question. Yes, I just made them online. The core slides were there, but for some reason the link was not active. So as I was posting these slides just before class, I posted those as well. So they should be all up to date now. Okay. Yeah. So, okay. So today we will actually do a very broad, high-level introduction to a whole slew of middleware systems. Okay. We are going to spend only a short amount of time on each, just to give you some flavor of what these commercial systems look like. The concepts that underlie these systems we already covered in class. By this time, you should know all of those concepts, and this is just for you to understand how some systems actually instantiate this concepts, and how you can use them to build more complex distributed systems. Okay. And towards the end of the class, depending on how much time we have, I'll start talking about, again very briefly, distributed data processing, which is Hadoop and Spark and so on. At one point I actually covered these topics in more detail, but now there's a separate course on this. It's called Systems for Data Science, where this is covered in a lot more depth. So I have to avoid repetition, I have reduced the coverage of these topics in this class. Okay. So let's get started with distributed objects. So all of you remember this figure from lecture 3 or lecture 4, when we were talking about remote procedure calls and remote method invocations. This is the RMI figure actually. And you know that there's a client, there's a server, there's an object at the server. Clients can then make remote method invocations on these objects. Okay. That gives you client server programming using RMI. Okay. When you make these objects distributed, then many things can happen. Okay, you might actually have different objects distributed on different machines. You can have the same object replicated on different machines or partitioned across different machines, and so on. And there are many systems that implement this functionality, and we are going to see a few of them in today's class. So let's start with enterprise Java beans or EJBs. Okay, I'm assuming many of you have actually programmed in Java, are very familiar with how Java works. Okay, typically, when you write a program, you will write a class. The class will have methods, it might have some data, or there may be many classes. When your program runs, the classes get instantiated as objects. Okay. When your program terminates, all those objects are gone. Okay. The lifetime of an object is the same as the lifetime of whenever the object got instantiated to when it was terminated, or when the program itself terminated. So these are transient objects in some sense. Okay. Now, when you write enterprise applications using Java, and these are applications that you deploy in companies and so on, okay, you get additional features from Java. You get all the features that you get in the Java you're already familiar with, but enterprise Java has some additional features. Okay. One of them is called a bean, okay, which is why it's called enterprise Java bean. And what a bean is a special type of an object that is persistent in nature, not transient. Okay. That means when you shut down your program, that state of the object is automatically saved on some persistent storage, such as a disk. Okay. And when you resume the program, or when you restart that program, that state can be reconstructed and you get the object exactly the way it was in the previous iteration of that program or the previous instantiation. Okay. So that is essentially what you mean by a bean. It's a special kind of an object that allows you to do this, and the runtime will do this for you. Okay. So now you can use this to basically have state persist across multiple instantiation of the program, or your state, which typically would mean you keep it on files on disk, is now given to you for free. Internally, the object state is still saved on disk across invocation. Okay. If you know Java serialize, deserialize, okay, essentially those are the operations that will be used to take the state, take the object, deserialize it on disk, and then reserialize it at a later time. Okay. Now, that is what a bean is, but then EJBs also have many other features. They have many other services that the middleware is going to provide for you. Okay. So, you will see that there are services like JMS, with Java messaging services, gives you message queuing like abstraction. There is JDBC, that is essentially a layer that allows you to connect that Java program to databases. Okay. So, this is the standard way you can take a Java code and talk to various databases in a data platform independent fashion. Okay. So, you can connect to different databases, and then you of course have the standard RMI interfaces and so on and so forth, and then you will see up there are objects that are instantiated as EJBs or enterprise Java beans. Okay. So, there are many aspects to enterprise Java beans, and the way you typically write this is a very standard object oriented fashion, where you have a separation between the interface of a class and the implementation of the class. Okay. That is a very standard object oriented way of writing code, where you define the interface, okay, and then the implementation is written separately that basically uses that interface, but the interface can be imported in other programs and so on, so that you can invoke objects on that or invoke methods on that object. Okay. So, the same kind of concepts are true here. There are many different kinds of beans that you will actually see within EJBs. Okay, the one that I was talking about are essentially called stateful session beans, where they have state for each session. Okay, and that state is persisted, so you can actually have variables associated with your class, and those variables are persisted on disk, and you can reconstruct them at a later time. Okay. You can also have stateless session beans, where your session itself is stateless, but there may be other kinds of things that you might need associate with the object, which is why you want to persist it on disk and so on. And then there are essentially entity beans and message driven beans, which are just used for communication between objects. Okay. So, that is a very high level overview of one middleware system, which is essentially EJBs. Okay. At one point, this was a very popular way to write enterprise application, web based application effectively, because they gave you web interfaces and so on. These days you use many other frameworks, web frameworks to write this application. So, EJBs are still quite popular in commercial environments, but that is not the de facto way by which you are going to write a web application today. But this can be used for other kinds of applications that are not web based, just two distributed applications communicating with one another to implement some higher level functionality. Okay. Now, predating the design of EJBs was another middleware system. Okay. So, we are going a little backward in time here, and that middleware system was called Corba. Okay. And again, this is not very popular today, or there are some remnants of it that are used, and I will mention a couple of scenarios where they are still used. But let me try to explain to you some of what Corba actually gives you. You will see that unlike EJBs, which are simply additional features that you now get when you write Java code, Corba is a much more complex middleware. It has lot more additional features than you would see in any typical programming language. Okay. But at the heart of Corba is what is called an object request broker, or an ORB. Okay. So, think of it as essentially the layer that enables all parts of your distributed application to communicate. It facilitates communication between components. Okay, so you will see that orb is essentially, it's also called a message bus in some terminology, if you heard the term message bus. So you will see that there are actually application code, there are all sorts of services that Corba actually provides out of the box. They are all going to use the orb to communicate. Orb is essentially the middleware layer that enables all of these things to actually occur. Okay. It also does other things, which is it handles distribution, it can handle heterogeneity where you might have different components running on different platforms. So it will allow you to communicate across different platforms and so on using XDR types services. Just to give you some sense of what these services are, okay, I mean we can just take a look at this table and you will see, I mean, we will not go into every single one of them, but what the designers of Corba did were ask, if I were to write a distributed application, okay, what kinds of things would I typically do? Okay. Can I take those functionalities and make it into a service so that when you write your application, you don't have to write that code, you just basically think of a service as also a library of some sort. I just use that library and I just use that functionality without having to implement it. Okay. So you will see many different things. So there is a concurrency service, which allows your code to essentially become concurrent. There is a transaction service that allows you to implement transactions using your application. Okay, you will see that there is a notification. We'll talk about the event service in just a moment, but you will see there's a security service that allows you to encrypt your RPCs or socket communication. Okay, there's a trading service which allow you to trade things between applications and so on and so forth. There's even a licensing service. If you want to sell your code as a commercial product, the licensing is actually implemented by Corba itself. So many different functionality that you could think of that are used in complex distributed systems. They essentially said, let's make it a library or a service, and then if you learn this middleware, you can just use the right services and build your application. Right? That will make it much easier for you to write your code, or so was the thinking. Right? Now it so happened that in making Corba a fairly heavyweight platform, they also significantly increased the complexity in the learning curve to write code in Corba, because you've got to now learn about all kinds of functionality that's in there, all the interfaces, and then use them in the right ways and so on and so forth. Okay, so that was one problem. Okay, it made your job, the learning of the framework, much harder. Okay, but once you learned it, maybe the amount of code you wrote was less, but there was a big learning curve. Okay. The second thing it did was also it made the platform very heavyweight and hence not very efficient in terms of performance and so on, because there was lots of communication between lots of services that had to be mediated through the orb and things of that sort that made it a fairly complex system. To even writing a small application meant you have to deploy a very heavy duty middleware, and then your small piece of application code would run on that middleware, which made the whole thing a lot more complex than it needed to be. Okay. So as a result, this was one of the first and early distributed middleware system. Okay. You will see that they thought of lots of the things that we have been talking about in this class, and they have kind of made them services that said that you can just use in your code. Okay. But because it was heavyweight, it never actually became a commercial success. Okay. Commercially, you don't actually see a lot of Corba code out there today. There are a few exceptions. Okay. If you have used Linux as a desktop and used the GNOME desktop manager, okay, that was actually built using Corba framework, where you had Corba objects and they could communicate and so on. Much more stripped down version of Corba, of course, but that was a way by which they said this is a nice abstraction for us to build of distributed application. In this case, it's a desktop manager, but there are applications that run on it that can use all of these functionalities and so on. Okay. So very few big successes because of the heavyweight nature of the system. But if you actually dig in a little bit more, you will see that if you this is the architectural view of how Corba runs on the client and the server, which is not very different from a very standard RPC or RMI like framework, where you essentially have a client application, you have an interface definition language that allows you to define interfaces that your application exports. You have an orb, which is like a stub, correct, but it does a lot more than what a stub code does. It also allows different components to communicate. And then underneath, you still have an RPC or an RMI like framework for your objects to communicate with one another. Okay, so it is still at the end of the day an RMI like system, but lots of services are built into the middleware for you. Okay. Any questions on this? Okay. So, I will now actually talk about one very specific. Okay, so let me say a few things before I talk about the event service. So, like in many RPC systems or RMI systems, even in Corba you can actually decide what kind of invocations or semantics are associated with RMI invocation. If you remember, when we were talking about RPCs, we said RPCs could be synchronous or asynchronous. If they were asynchronous, they could be deferred synchronous, one way, and so on. Okay. Corba actually implements all of those. Okay. So, you can say I want deferred synchronous invocations of all of my methods, or I want one way, or I want synchronous, and it will do the right thing for you. Okay. So, you can actually choose when you write your interfaces what kind of semantics you want to associate it with their invocation. Okay. Again, they said we can let the programmer decide. We won't pick one invocation semantics for our system. We will let the programmer decide. Okay. So, lot of flexibility, but also comes with some complexity. Okay. Now, there is only one service I really want to talk about in Corba, which I think is interesting because we have talked about this idea for early on in this course, and that is essentially the event service. Okay. The event service allows you to implement a specific type of distributed application called publish subscribe or pub sub. Okay. It is a very popular way of writing application, distributed application. Okay. So, you essentially have components that are called publishers or subscribers. Publishers can publish data or events, okay, and subscribers have to specify what kinds of data or events they are interested in, and then whenever the right type of data or events get published, it is delivered to them. Okay. That is how communication is actually going to take place. It is not RPC based, it is not socket communication, you just publish data or events. Okay. And in this case, the orb is actually going to mediate. You can have subscription saying I want all events that are updates to such and such data type. So, every time this table is updated, notify me. Or you can have any kind of subscription. Okay. Whenever that kind of event occurs, it is essentially going to be delivered to you. And the way this is, you can think of this logically is, there is essentially the middleware is providing for you what is called an event channel. Okay. Publishers, which are in this case labeled suppliers, okay, are essentially going to publish data. Okay. Then they are going to go into the event channel. Consumers have essentially subscribed to certain type of data. You could say send me all the data, or you can say, let us say this is a stock application. Okay. So, every time stocks of these companies get updated, notify me or push them to me. Okay. So, you can specify what data you are interested in, and then the event channel in this case is going to essentially send them to the consumers or the subscribers. Okay. We are going to use these terms. Publishers and suppliers are the same, subscribers and consumers are the same, they are synonyms in this case. Okay. And you can now imagine that the architecture could be using push or pull. Okay. What is shown in this figure is a push-push based event model. Okay. The publishers are pushing data to the event channel, the event channel is pushing the data to the consumers. Okay. You can also use pull. Okay. I think there is a figure here which is essentially doing the event channel is polling the publisher saying, do you have any need data to publish? Okay. So, you can keep polling, and the consumers are now polling the event channel saying, is there any new data that matches my subscriptions? Okay. That is a pure pull model. You can have any hybrid. Okay. Publishers can pull, subscribers can pull, and so on and so forth. Okay. So, this is, although we discussed this at a very high level of abstraction, it is important to know that this is a very popular way of implementing many applications. Okay. You will see more distributed systems, or you might have heard of open source distributed systems, things like Kafka and others. So, many of them use a publish subscribe like framework. Okay. And of course, they are not based on Corba. This is the Corba way of implementing a pub sub model, but the idea of a pub sub based abstraction to implement distributed application is a very popular one. It may not be based on Corba, it uses other abstractions, but it uses these ideas. Okay. So, the notion of publishers and subscribers. Any questions on this? Okay. So, I also want to mention that in the pull model, you can of course have synchronous or asynchronous. You can have callback saying if I am going to poll, but I will also register a callback. If a matching event occurs, then notify me. So, all of those nice features that we have looked at when we do pulls are all supported here using polling and asynchronous notifications. Okay. So, we are going to switch gears and look at yet another middleware. This one comes from the Windows world. Okay. It is called DCOM, which is now has evolved into .NET and things of this sort. Okay. So, there is a little bit of history here. So, the history also shows how this middleware systems actually evolved over the ages. Okay. So, what we have ended up with today was .NET, but maybe 30 years ago when all of this actually started, you started with something very simple which was called COM, and that became OLE, and that became ActiveX and so on. So, let me give you a little bit of description of what the historical evolution was. So, the very old days of Windows, or early days, no, not old, early days of Windows, the middleware system that was implemented in Windows was called COM. That basically just allowed you to do simple RPC style communication. Okay. So, COM was basically allowed you to do communication. So, essentially it had an object, you could invoke object methods and so on and so forth. Okay. So, that was a standard way you could write RPC application in Windows, was using the COM libraries. And then to enable Microsoft Office to do interesting things, what this evolved into was a layer on top which was called object linking and embedding, or the OLE layer. Okay, what this allowed you to do was have Microsoft Office documents that you could embed in other documents. Okay, so, you probably have taken a spreadsheet, okay, and put it into a PowerPoint as a chart. Right? And then if you actually double click on that PowerPoint slide, it actually opens the Excel spreadsheet, and then you can start editing it in Excel, and then you save, then the chart appears. This allows now PowerPoint and Excel as applications to communicate with one another. Okay, that is actually happening using COM. So, they are essentially using their RPC framework to allow, in this case, Microsoft Office applications to communicate with one another, to embed one Office object into another Office object. Okay. You can embed spreadsheets into Word documents or spreadsheets into PowerPoint documents, make figures and put them, and when you double click it, it actually invokes the right application, they talk to one another and so on and so forth. Okay. So, that was the OLE layer, and that is basically how they were using their COM libraries. And then when and essentially the web became popular, they added another layer on this which was called ActiveX, that allowed you to write interesting applications that were browser based. Okay. So, essentially you had ActiveX support in Internet Explorer, you could write applications that did the same kind of communication, but now you are using the browser to talk to a backend application that was running over COM and things of that sort. Okay. And then of course, those applications could only use Internet Explorer. If you used some other browser in those days, Firefox and other things, it did not work, because the ActiveX support was actually built only into Microsoft Internet Explorer. There are still to this date some applications that require you to use Internet Explorer, even though it has been deprecated, because it is based on ActiveX. Okay. It is not a web based standard, of course, there are better ways to write web applications, but that was essentially the way you could write ActiveX scripts. Rather than writing JavaScript, you could script it in ActiveX and so on and so forth. Okay. And now eventually all of this has now evolved into DCOM, which is take this is still essentially the lower two layers still sit on a single machine, okay, make it distributed. Okay, so, that is basically distributed COM, and distributed COM now essentially became .NET, where it is now language independent. Okay, so, you can write different components, you can write something in C#, you can write it in Java, Visual C++ or C++, and have them all talk to one another. Okay, so, it is now even language independent, different parts of the application can be written in different languages, and then your .NET layer will make all of that work. Okay, so, that was essentially the equivalent of what Corba had tried to do in the old days, which is what .NET now actually does, still for largely Microsoft Windows based platforms, but a lot of it is not necessarily Windows based anymore. It works over the web and things of that sort. Okay. So that's the history of how all of these concepts that we have actually studied in this course have actually been instantiated in the Windows world. Okay. Started with COM, then you have a OLE layer, then ActiveX, and became DCOM, which has eventually became .NET. Okay, so that's essentially what is said here. I'm going to skip this slide and show you typical client server machine in the DCOM world. And if you look at this, this looks no different from all of our standard RPC, RMI type frameworks. There are some additional components here. There's a registry, just as your Windows registry. There's a service registry where you can actually register your objects. Okay, that's the database. That is actually the directory service. You can actually load them from the registry and so on. But the rest of it looks very similar. So you will see that there's a proxy and marshalling layer which is going to marshal, demarshal arguments. The COM layer is essentially your stub in this case. That's allowing you to communicate, and then you see that there are client application, there are objects, and you are making RMI calls. Okay. So across all of these platforms, you'll see the concepts are the same. There are some differences in each case, but what we have studied actually applies to whether it's the Java world, whether it's Corba, DCOM, and we'll see some more. Questions? So there's one more thing I want to say, which is the equivalent of what beans do in the Java world are what are called monikers in the DCOM world or .NET world. Okay. So they're essentially persistent objects. By default, any object, any class that you have, that instantiation object, makes it transient, which means that object lives in the memory of that process. When the process terminates, the object is gone, all of its state is gone. If you want the state of the object to live beyond the lifetime of a process, you have to make it a persistent object, and you're going to use a special type of object which is called a moniker object, which will again automatically allow the runtime to save that object state from the process memory to disk, and then you can use a handle to reinstantiate it, and it will appear in some other process's memory. It will look exactly the same as it was before. All the state gets reconstructed. Okay. So you have that same concept which is there in EJBs, also in DCOM and .NET. You have to basically create this special type of objects. Okay. All the other objects are no different, so I'm going to ignore them. But this is the only one that you need to know is somewhat different from normal objects. Okay. So that was a very high level broad brush introduction into how middleware systems work in the Java world and the Microsoft world and elsewhere. Okay, what we'll do now for the next maybe half an hour or so is talk about a very different kind of middleware. Okay, something that you probably have not encountered, which are called coordination based middleware. Okay, so we'll talk about what they are, how they work. We'll look at a very specific one which is called Jini. It's Java based, but it's actually designed to do distributed coordination. Okay. So let's try to understand what this is. Okay. So to understand that, let's try to see how you can take different applications that actually communicate and classify them into some taxonomy. Okay. So if you think about how two applications communicate, okay, you can think of their communication as being coupled or decoupled in space and time. Okay. What does that mean? So to be coupled in time essentially means both components of the application have to be running at the same time for them to communicate. Okay. If they are decoupled in time, that means they don't have to be running. Okay. When we did message queuing systems, the two endpoints did not have to be running at the same time. They could send a message, the message could be stored and it could be taken, that message could be taken later. That means the application components were decoupled in time. They ran at different points in time and they could still communicate. Okay. When you send a socket message or RPC message, both the client and the server are actually running and the communication is happening, that's coupled in time. Okay. Now, so the same thing you can think of from a spatial perspective. Okay. When you are coupled in space, that means that you know who you are actually going to be communicating with. When you are decoupled in space, you may not know a priori who you are going to be communicating with. Okay. So let's think about decoupled in space. What is the example that we can try to relate to? So think of a a meeting that you call in a meeting room. You send an invitation to a group and say we are going to meet at 5 to discuss maybe the final exam or review the final exam. Okay, now you don't know who is going to show up, okay? But you know that they are all going to show up in that room you specified that let's meet here. So you know that you specified a space, but you don't know who is actually going to come, okay? Because that message was not addressed to any one person, it was addressed broadly. Okay? As opposed to you sending a specific email message or a text message to a specific user, you are actually directing that message to someone specific, okay, as opposed to addressing a message which is now sent to anyone. So that's basically referential means space. So being decoupled in space essentially means that you are going to be in this box where you're coupled in time. You will all meet at 5 o'clock to talk about the final exam. Okay, so it's synced in time, but you have actually don't know who might show up because that message was meant for anyone. So that's meeting oriented. The last box here says that you could be decoupled in time and space. That means you are communicating with entities that may not all be running at the same time. And when you send a message, it's not addressed to anyone in particular. It's a generic message that can be taken delivery by anyone they feel is important to them. Okay. So that's the quadrant we are actually going to focus on for this for the rest of this lecture, or maybe at least half of for the remaining 20 minutes or so. Okay. So that's called generative communication. Okay. So it's instructive to understand how this might even work. Okay. What are some examples that we can relate to? Okay. One way to think about this is what are called blackboard architectures or bulletin board architecture. Okay, so let's take a very specific example. Okay, let's assume that you are going to graduate and you want to essentially sell your furniture because you're moving somewhere else. Okay, what do? Okay, you typically make a flyer saying I'm selling my whatever sofa or whatever the furniture is. You go put it on some bulletin board. Okay. Now, is that message addressed to anyone specific? Okay, you just put it on a bulletin board and you hope that somebody who is interested is now going to take a look at the phone number you stuck, take that phone number and call you. Okay. So, essentially you have now communicated with the group of users without knowing who is interested in your message, okay, by essentially posting a message on a bulletin board. Okay. Now, note that the communication is not coupled in time. You put your message on that bulletin board announcing sale of your furniture at some time. Some person might come 2 days later and actually take delivery of that message, might actually see that message. So, it's not coupled in time. Okay. It's not spatially coupled because you're not addressing that to anyone in particular either. Okay. So now you are enabling communication where the parties don't know that they are actually communicating with one another a priori, neither are they actually communicating at the same time, in point in time. Okay. So if you use this concept to design distributed application, you essentially have application components that are decoupled in space or time. Okay. And this is called generative communication. It's also called blackboard architectures for designing. That's a middleware term. Okay. So it's essentially blackboard or bulletin board model. Okay. So let's understand now, take that idea of having a bulletin board, say how do you build an application? What does this mean? Okay. Why would you ever want to design an application to do this? Can we think of some scenarios to where an application is built using a bulletin board architecture or a blackboard architecture? Yes.
Did you just say that like Craigslist was able to virtual bulletin board, something of that nature, or do you mean more at an architectural level?
Well, I meant a real system. Where would you use this? Not like now a bulletin board of Craigslist is another bulletin board. Yes.
Maybe you could think of a smart refrigerator as a bulletin board system. Physical items go in, look at the list of things that you want to add.
Okay, smart refrigerator.
You need to buy this stuff, you're running out of this, so you kind of have a state of what the current objects are. I need milk,
Okay. Possible. I have to think about that. Smart fridge. We are building one, but we'll see.
If you have jobs that you want to assign to workers, you could have bulletin board, job list. Workers could pull the bulletin board, could pick a job,
Okay.
fill in a service request.
So you have to advertise, you have some set of jobs, you post that on a bulletin board, workers come and take the job. That's a good example. I'm going to come back to that. You had something to say? Blockchain. Blockchain, we'll come to blockchain next week. I do not think it's bulletin board necessarily, actually, because it's not, it's a transactional model that uses consensus and things of that sort. Yes. Yes, all of those things are true, but having said that, it's not necessarily what you are going to be seeing here. Okay, when I explain this, you can come back and ask me if this is going to map to blockchains or not. You had something to say? Okay, so you're describing a scenario where there are front end as a back end, they're using some sort of a bulletin board to communicate with one another. So if I were to paraphrase what you said. So any other thoughts before we move? Yes.
Protocol, like for example, weather app or something like where everyone requests actually similar to startup, they use this account weather status for instance.
Right.
And someone updates it, send it.
Okay, weather application, you can post weather information, whoever wants to come take a look at it will look at it, right? So these are all good ideas, and if you think about what is common across many of the examples that were given here, you will see that what is actually happening is the bulletin board is being used to advertise some service. Okay? You may not know who is going to consume this service, but you might say, I am going to advertise this service, or I have this information to share with everyone. I am selling my furniture. Okay? So here, and there are many examples where you could advertise these services. Okay, this bulletin, one very concrete use case of bulletin board architecture is, let's say you walk into a new environment, a new network environment. Okay? Now you don't know what all things are there in that environment. Maybe you want to print, okay? But you don't know what printers are available. What if every printer in the environment had published a note saying, I am a color printer and this is my IP address and this is my mod. Because all you have to go is, if you want to print something, you go to this bulletin board saying, is there a print service available? And you might get a list of printers. You can query and say, here are all the printers available. Okay, or you might ask for some other kind of service. Okay? So this is basically used in many of these scenarios where you want to advertise some service as a distributed system. Your clients might come and look for these services at some later date. It could also be some data, it doesn't have to be services. And then a match is made through that bulletin board, and then you can basically compute or do whatever it needs to be done. Yes, you had something?
So that example, is that different from a naming service or is that essentially what it does?
Okay, the question is that different from a naming service? In some sense, it's a lookup based mechanism. Okay? There are some differences though, in that in this case, you are basically, you don't know a priori who you are going to be communicating with and so on. Okay? When you did RPC lookup, there was a similar thing where you had registered a service with the RPC lookup naming service, and clients came later to look for that service. Okay? Very a similar idea in some sense, but a little more generalized, because this is going to be long lived, and you will see that it is built with a database and so on and so forth. Okay? So it basically, the scenario I mentioned, which was one use case of bulletin board architecture, is called zero configuration. Okay? Where you don't want, in the printer case, you don't want users to manually download a driver, configure it, and so on. All of that information is automatically configured for you. Okay? So there's a discovery that actually happens through the bulletin board, and configuration that also happens to the bulletin board in that very specific example. So, there are many such use cases where this kind of scenario is useful. Okay. Now, when we are going to look at a specific bulletin board architecture which is called Jini. It's a Java based middleware that enabled this to happen. And their idea in the old days was not unlike the smart fridge that was mentioned. They said we might have all sorts of intelligent appliances. They need to, you don't want a homeowner to say, here's a smart fridge, that's its IP address, let it talk to something else, and here's my reference. So, they all want to discover one another, figure out who is there in the environment, decide how to talk to one another, have them auto configure, and so on and so forth. So, that was, so they had started with the intelligent toaster. Okay. Why they thought that should be the thing to make intelligent, we don't know, but that was their example. Okay. Not a fridge, but they said we'll start with the intelligent toaster that will discover maybe the clock, and the clock will tell it when the alarm is set, and the toaster will turn on, or a coffee machine will turn on when you wake up, or something along these lines. Okay. So, now your applications that when you write the code, you don't know who you will communicate with. So, you are not designed it saying I will communicate with this component. I just advertise my services, you discover services, and you communicate based on what you discovered. That is the basic idea. Okay. Now, it also uses, if you can now relate to the pub sub model, you can see that you are, by advertising a service, you are publishing a service to a bulletin board. Okay. And when you go and query for a particular type of service, you are consuming that service. So, at a high level, although this is now decoupled in space and time, it uses concept from a pub sub type architecture. Okay. So, here is how Jini works. Okay. So, it essentially has what is called a tuple space or a Java space. Think of it as a logical database. Okay. It could actually be implemented using a real database. We don't care. We just think of it as a tuple space. This is our bulletin board. This is where we put notices. Okay. This is where we advertise services. So, you will see that application essentially has put a note A, okay, saying I am a printer. So, I am, or then that one has written B, and so on. And then that application comes along and says, look for all tuples or all entries that match this criteria. It's like a database query. Show me all printers. That is a query. You will then go and look at all your tuples, all of these records, and say what are entries that match. Okay. And then you can optionally take that note off or just leave it there. That is an option, because if you just discover a printer, you don't want to delete that note, but if you might be consuming some data item, you delete that data item from the tuple space. Okay. So, at the heart of it, this looks like essentially a database where you are posting records and you are querying records, but the way it is done, it allows you to build this middleware, and distributed applications can be written on top of this. Okay. This tuple space that I have shown you here can be implemented in many different ways, and I will show two examples of how this is implemented. This is called a Java space, by the way. Okay, tuple space is just a term that says that it's like a key value store. Okay, you can have tuples that you can post and remove. Okay, so that is the same example where you just did a query, but let us look at some examples of how you can implement it. Okay. So, at the top you have essentially a tuple space where that is fully replicated. Okay. Every time you post a note, you have to post it in all the replicas. Okay. When you want to read it, you only go to your local replica and read it. Okay. So, think of this as you have a bulletin board on each floor of this building. So, when you post a note, you go and post it everywhere. So, then I just have to look at my local note bulletin board to look for all notices of interest. Okay. So, writes are replicated, reads are local. Okay. The lower one is a partitioned tuple space where each bulletin board might have different notices. So, when I write, I will write to my local one. I will just post a note to my local bulletin board. Different ones will have different notices. So, when I got to read, I have got to query them all to find if there are matches. Okay. So, one will basically broadcast reads, the other will broadcast writes, but the other operation will be local. Okay. So, you can implement your tuple space in either of these ways depending on what you are trying to do within Jini. Yes, question. Okay. How does this relate to Zookeeper? So, Zookeeper is essentially a locking service with consensus and things of that sort. Okay. This is simply think of it as a replicated database. Okay. It is much simpler than anything that Zookeeper would do. Because Zookeeper is used to implement things like distributed locking or even do consensus. Okay. Yes, you can certainly. Service discovery is not unique to distributed coordination. So I was just giving an example saying you can use it to do service discovery. There are many other ways to do service discovery. The standard way in LAN is that you are actually broadcasting a packet and it's going to all the machines. So if you want to listen for a DHCP server, that's done using broadcast. There is no place you advertise yourself as a DHCP server. So that service discovery is orthogonal to how you actually do this. There are many ways to do the service discovery. This is just one way. Zookeeper allows you to do it, and so do other systems. Any other questions on this? Okay. Okay, so this is essentially our partition where you are going to do local writes and global reads. Okay, so that's basically Jini, and the remaining time I am going to now actually talk a little bit about MapReduce and Spark and things of that sort. Okay, so let's start with big data processing. So I think you have some idea about what these things are if you have taken systems for data science class, but if you haven't, bear with me. So one of the big applications of distributed systems is to essentially use a very large cluster of machines to process large data sets. Okay. And there are many application domains where this has become important. So you will see here, you essentially have medical images, you might have genomic data, you might have financial data, clinical data, you might have all sorts of sensor data and so on. So you have a very large data set, and the question is how can you essentially process this very large data set very quickly. Okay. So given some of the concepts that we have studied in this class, you should say if you have a large cluster, why not parallelize the processing of that data set. Okay. So that is what many of the platforms that have come up in the past 10 or so years essentially do. So you start with a large data set, you chop it up into smaller chunks, okay, and then you essentially give that chunk to a machine. That machine is going to process that chunk, produce some intermediate result. It may get passed on to yet more machines that will take intermediate results, process it further, and so on and so forth until you produce the answer you want to produce. Okay. So that's essentially the basic idea that underlies all of these distributed data processing platforms. We are essentially going to look at two examples. One is MapReduce and Hadoop. Okay, and then we are also going to look at Spark, which improves on Hadoop performance by using data that is stored in memory and so on. Okay. So here, if you don't know what MapReduce is, this is going to give you a quick one slide overview of what the MapReduce programming model is. Okay. So MapReduce data processing uses two phases to process a large data set. It's called the map phase and the reduce phase. Okay. And this is best explained with a simple example. Okay. Let's say you have a very large data set which is shown in these white boxes at the top. Okay. And we could just say it's a bunch of documents. Okay. You basically went and crawled the web and collected a bunch of documents. Okay. And we are going to now use MapReduce to implement a simple thing. You can do many things with it. Let's say you could do word count. You want to count every word and the frequency, how many times the word occurs in all of those documents. Okay. So how would you do this? You have a very large repository of documents. You are going to chop it up into smaller pieces. Each of them is going to get processed in parallel. And here we have actually 3 machines that is going to process that in parallel. Okay. So you will take the first snippet of a document. You will basically look at all the words in that document. You got to count the words. Okay. How would you do it? Using MapReduce. Yes. Okay. You could do it many different ways, but first of all, you got to understand how word count is going to work. So you got to keep a big table. Every word you encounter has to be put in the table. Every time you re-encounter the word, you got to increment a variable that basically counts how many times you've seen the word. Okay. That's how you are going to do word count, except that here you got to do this in parallel. Okay. You don't have one machine that's sequentially scanning and counting all the words. Okay. So there are many different ways to do this. Okay. So here's one way. You can say basically I am going to take my key namespace, which is all the words that exist in the, let's say, English dictionary, and partition it into bins. All words maybe A to F are essentially going to be sent to this node. All words from G to something are going to be sent here. So this node is responsible for keeping the part of the table that goes from all words from A to F and so on and so forth. So I partitioned my job. Right? So in this case, all I'm going to do is whenever I encounter a word, I'm going to say which node should I send it for subsequent processing. Okay? So if the word starts as the first letter is between A and F, I'm going to send it here, or I'm going to send it there and there. And then each of those is going to maintain part of the table and count. Okay? That's one way to parallelize it. I could do more. So in the map phase, simply my map phase is simply hashing saying which node should I send it to. Okay? And I sent it to that node. And that node does all the count. You could of course do something what was mentioned here, which is I do a little more processing here. Okay, I could actually take that little snippet, I could make a local table and I can count all the words in there, and then I partition that table and say all the words A through F I encountered actually go here. So I don't need to do, all I need to do is merge those results with the results I already have. Okay? So on and so forth. I can divide up the work in any different way, but I essentially at the end of the day I parallelize the work. The more nodes I can throw at it, the more I parallelize, because I can take my entire repository of documents and I can process it in parallel. Okay, there are two phases in this. Okay, the map phase is doing some processing, the reduce phase is doing more processing. Okay, so a two-phase process. Is this clear? Okay. Now you can generalize this and say that rather than, and the other thing I should say is, between this is the map phase and this is the reduce phase, and you will see all these black arrows. That's called the shuffle phase. Okay? In the shuffle, data is actually going from map nodes to different reduce nodes. Okay? Depending on what data you're encountering, you're might send them to different, in this case, the word might be sent to node 1, node 2, or node 3, depending on what it is. Okay? So that's the shuffle. So there's a lot of data exchange happening here in the shuffle phase. Okay? So, and then you are going to produce the final answer as the output of all the reducers. Okay, this is an example of a two-phase data parallel or data processing platform. You can generalize this in many different ways. Okay, you can say why stop at 2. Okay, you can have different nodes that are doing some processing that basically produce intermediate results. They send to other nodes, they process it, they do more of this and so on. And you have now a DAG of processing nodes, not a two-phase node thing where essentially you will have nodes that produce data. They might send this to other nodes that might communicate in some arbitrary ways to produce the final answer. Okay? So you can think of this in a more complex setting, and you can have, so there are other data processing platforms that allow you to take your overall computation and make it a DAG rather than a two-phase process. Okay? But at the end of the day, what you have essentially done is taken all of your work, split it across nodes, parallelized it, and so on. Okay? And different data processing platform will do it differently. This one is called MapReduce. A popular way it's implemented is Apache's Hadoop framework, or there are other frameworks that do the same thing. Okay? So essentially, if you now take it and make it a DAG, you will have Microsoft framework, Dryad, Naiad, and so on. You can essentially turn that DAG into cyclic graph, then you can essentially use something like Apache Flink, where you can reprocess the data. Okay, you can essentially have cycles in it. So you will have other frameworks like Apache Flink. And if you have data that's coming in continuously rather than a data set that's already been given to you, then this becomes what is called stream processing. In stream processing, data is streaming to you. It's not that all the data is already there and I just process it, and when I'm done, I can just stop. Data is continuously arriving. You have the same procedure. There's a lot of data flowing in, you partition the processing, and then you process each of the stream of data. And there are many systems that are going to do this, which are Spark streaming, Kafka does stream processing, so does Flink and Naiad, and so on and so forth. Okay? So you'll see that there are many different frameworks out there. MapReduce is basically the simplest one. Okay? You can make that processing from two phases to a graph. Okay, that gives you other frameworks. Then you can essentially, we'll look at Spark, which does this in memory in just a moment. You can have other kinds of processing, and then if you basically go from batch to streaming, you have yet other kinds of systems that do this. But they will all have this thing in common where you take the work, partition it across nodes, and leverage parallelism. Okay. Any questions on this so far? The people used MapReduce, Spark. Okay. All right. So now, if you actually look at some Apache's Hadoop platform, you will see that there are many different pieces, and I'm going to show you a picture to show you how all of this works. Okay. So first, there has to be a storage layer where you store this large data sets. The last time we were talking about file systems. Okay, we talked about HDFS as one of the file systems. So the standard database layer for Hadoop is actually HDFS, but you can plug other file system. It doesn't have to say that all the data stores in. This is a distributed file system that essentially takes the same idea. You take your large data set, you make smaller chunks, you distribute it across disks, across multiple servers. So now you are leveraging the storage space on multiple machines. Okay. That is what HDFS does. We talked about that last time when I covered HDFS, Google file system, and so on. Okay. So that's basically the storage layer of this system. Okay. On top of this storage layer is the resource management layer. So there are things called Yarn and Mesos, which are the two popular frameworks. And what they do is they essentially allow you to take a cluster of machines and allocate a subset of them for a certain task. Okay. Maybe you are not the only user who wants to process a large data set. Maybe there are 5 other users, each of them want to start a MapReduce task. Okay. So now you have to make smaller groups of nodes, each of them is going to run one MapReduce task. How do you do that? You are going to essentially use Yarn and Mesos to instantiate a MapReduce task or a MapReduce cluster that is going to run one job. Okay. You can have, if you have lots of machines, you can have smaller groups of them processing a separate data set altogether, and you can control how many machines go into cluster 1 that's processing this data set and how many go into cluster 2 to process some other data set. You can allocate and deallocate machines and so on. Okay. So this is our resource management layer. Okay. On top of this, you will see that you basically have the actual data processing framework, and we talked about MapReduce, but you can actually, if you look at the ecosystem, you can plug in others as well, because you can say for this I need to use MapReduce, but this other data set is streaming, so I'm going to use Flink. Okay. But you use so you have a collection of machines. Some of them are running MapReduce jobs, some of them are doing stream processing, and so on. They're all managed by the Yarn or Mesos layer. Okay. So you don't even have to pick in a large complex system what type of data processing you are going to do a priori. Your system will support multiple, and you can say this is the kind I need for this job, and then you can say this data set is going to be processed by MapReduce and so on. Okay. And then there are higher level applications, which is what you are going to use to write your code to do the data processing, because you got to say this is the code that's going to run on MapReduce. There are many applications that do this. There are language specific extensions for this. You will see that there is something called Hive, Pig, Latin, and so on. Okay. None of which we have covered, but something you should know about. Okay. So it's a complex system. Okay. The slide that I showed you previously only looked at this part of it. Okay. But you will have to see that there are many different things that have to come together to construct this distributed data processing platform. Any questions on this? Okay. So I already mentioned all of this, so I'm going to, and then there are of course newer frameworks that are also getting plugged into the ecosystem. If you actually used things like TensorFlow to do machine learning or MLlib or graph processing, they're also getting plugged into the same kind of framework, because TensorFlow also does distributed processing to train over a large data set, for example. It's the same kind of scenarios apply in the case of machine learning processing as well. Okay. So I'll take another example, which is Spark, and show you a little bit about what Spark does and how is it different from what Hadoop or MapReduce does by default. Okay. Hadoop is designed for batch processing. Okay. The data is all already on disk. Okay. We want to parallel process all of this data and produce some answer. Okay. And because it is batch processing, typically you are willing to accept longer times for the data set to be processed. First of all, if your data set is large, it is going to take you a long time to process it. Okay. So it is designed for batch processing scenarios, which means that during the shuffle phase, for example, if you produce a lot of intermediate data, you can store that data on disk, and then the reducers can read it from disk at a later time and process it, and so on and so forth. So there may be a lot of I/O operations that, and you should know by now that I/O operations are slow. So as a result, when you're doing this kind of large scale data processing in batch mode, it might take a long time for the job to finish. Okay. So what Spark, the main insight in Spark was, for many data processing jobs, okay, you actually care about the latency or time it takes you to process that data. Okay. So to reduce the time it takes you to process a large data set, okay, what is one simple thing you could do? Okay. And that what they said was important was to reduce the amount of I/O that your job performs, because I/Os to disk are slow. Disk I/O is a slow operation. The less I/Os you have, the faster your processing is going to be. Okay. So then the question is, how are you going to do this? Okay. The way you are going to do this is you are going to exploit the memory on the machines. Okay. You are going to store intermediate results in RAM rather than going to put intermediate results on disk. Okay. Or so the argument was. So it said, let's do distributed data processing. We'll have the same kind of thing that MapReduce does, but all the intermediate results that are being produced, let's say at the end of map, etc., we'll try to avoid spilling them to disk. We'll just stuff them into memory somewhere, and then we'll read that from memory. Okay. So they came up with this notion of RDDs, or resilient data sets, and this is basically an instantiation of what is a more general concept, which we didn't cover in this class, but a more general concept, which is distributed shared memory, okay, or DSMs. Okay. So if you actually took this class 20 years ago, okay, DSMs were a very popular topic. Okay. DSM says, let's take memory on all the machines and make it one logical pool. So I can now store my data not on this machine, but any arbitrary machine. I can then go and actually take data from that machine, and so on and so forth. And that concept was called distributed shared memory. I'm sharing the memory across machines to construct a larger pool of memory, just as a distributed file system shares disks across multiple machines to construct a logical file system that spans multiple disks. Okay. But DSMs for a long time never went anywhere. There are lots of papers written. Nobody used it because by definition going to a memory on another machine was slow. It involved a network hop. Okay. So there were no real applications that used it for a long time, and DSM, basically that topic was removed. So in fact, you will not see it in the book anymore. But if you take the version of the book that was existed 20 years ago, you will see a big chapter on DSMs. Okay. So why am I saying all this? The reason is, what Spark has essentially done is, by coming up with this notion of RDDs, it has actually made DSMs a practical thing for a very specific use case, which is to process large data sets. Okay. You are not constructing a general middleware where you have a pool of memory you can use for arbitrary application. You are constructing a very specific use case where I process data in parallel. All the intermediate results I'm producing, instead of storing it on files on disk and having the next stage pick it up from disk, I'm actually going to construct a data structure where I store it, and the next phase has to then come and pull it from that data structure. The more data I store in memory, the faster my processing will run, because there's less I/O involved. Okay. That's the basic idea behind what Spark did. That was a big step forward from the way most of the data processing frameworks work. They all basically assume it's fine, there's a lot of data, let's put it on all the intermediate results on disk and read it in each phase. Okay. Spark said that's a bad idea. Okay. It takes long, so let's put it in memory. Okay. And doing so, they essentially sped up data processing and opened up new ways of actually processing large data sets that was not considered before. Okay. You can essentially do what is called SQL, standard SQL queries on large data sets. Okay. You can do interactive visualization, interactive mining. Okay. You can essentially run a query, and because it's running in memory, you can expect answers in minutes rather than hours or days. Okay. Not on very large data sets, but reasonable sized data set. Okay. So you can actually do things that you couldn't do with MapReduce because it took much longer. So as a result, Spark has actually become a very popular data processing platform that has subsumed a lot of what Hadoop and others were doing. And you will see now there is Spark SQL that allows you to actually do SQL queries. There's Spark Streaming, where you can actually essentially use Spark to do streaming. Okay, Spark is also used for doing machine learning, although TensorFlow seems to have become more popular than Spark for doing ML, but there's still a lot of ML actually happening on the Spark context as well. There's a competitor to TensorFlow and Caffe and all these other things. And you can do graph processing and so on and so on. So it's emerging as a more generic data processing platform, because if you have fast parallel data processing or distributed data processing, you can use it for many different scenarios, and that is essentially what Spark is essentially ended up doing. And it is backward compatible in that it actually would also run things like Hadoop jobs. Yes, question in the sorry. Okay, how is it resilient? I have not actually talked about what RDDs. I just explained the concept. I will talk about that in just a moment, because that's here. Okay, so you will now see this example. Okay, so you will see now this data processing is now a DAG. In this case, you will essentially have your initial data set gets loaded in memory. Okay, if let's say you have it on HDFS, the first thing is load it in memory, so it all appears as RDDs, which is essentially the same data set now sitting in memory. And then your first phase begins. It starts processing this in parallel. You produce some intermediate data that you put back in memory, and then you do that and so on. Okay. Now, each of these RDDs are essentially, think of them as shared memory data structures, where any machine that is part of the Spark cluster can go and access it, saying I want this data from. So think of it as a remotely accessible array or a key value store, where I can just go and pick data from it. Okay. So that's essentially the concept of shared memory. Okay. Then the question was asked, saying what is resilient about this? Why is it resilient? Okay. The reason it is resilient is, the one interesting that Spark did is said that there can be failures in this pipeline. Nodes can fail. Okay. Power may go out. Okay, so I have a large data processing job. Okay, what should I do to essentially reconstruct that computation? Okay. So Spark does something interesting, which is it essentially keeps track of the processing that has been done so far. Okay. So it keeps track of this RDD data structure was derived from this one. Okay. And this one was derived from has two parents and so on and so forth. Okay. So at any point, if some machine fails and you know what RDDs were stored on it, it basically has the what is called the lineage graph. It knows what are the ancestor RDDs it depends on. Okay. And then essentially it only recomputes those computations that it needs to redo to reconstruct that data. It doesn't go back to the beginning saying that node crashed, let's throw out everything, let's restart everything from the beginning. You don't have to do that, because you might still have some of these older RDDs kept in memory. So I just have to take those and redo the computation from that point on. Okay. So in that sense, they are resilient because they can be reconstructed if there are failures in the system. Okay. So that's basically the idea. So you are going to track your computation. Okay. If there's a failure, you are going to say this data is lost from memory. Okay. And of course, the recomputation, you have to restart the computation. But then say, how do I reconstruct that data structure? Say, I have already tracked how it was derived. I know what code was run to actually construct it. So I go back to the most recent set of RDDs I have and redo the computation from it. It's almost like saying when we did distributed snapshots, I roll back to the most recent snapshot and only restart from there. That kind of idea is not a real snapshot, but it acts like one. Okay, your question. How is the problem of network latency? Yes. Okay, that's a good question. The question is, if 20 years ago DSMs were not considered successful because there's a network latency, what has actually changed? That's your question, right? So is that the technology has improved to a point where accessing, this is a very standard calculation, because now you have 10 gig Ethernet and even 40 gig Ethernet and whatnot, very fast networks. Right? So the latency to access a memory page on a remote machine is actually faster than making an access from local disk. Okay. If network is slow, then network hop and disk latency become equal. Local memory is always fast. Remote memory involves a network hop plus remote memory access on that machine. If the network becomes fast, that latency goes down, where it's actually advantageous to go and access somebody else's memory rather than keep that data locally on disk. Okay. So, because these technology trends keep changing, some of these ideas that did not make sense many years ago now suddenly become feasible. Okay. And the second issue is, you are not actually comparing local memory to distributed memory. You are still trying to say, I want to avoid slow IOs. If I had taken each of these outputs and actually put them on disk and had the next stage and go read it back from disk, that would be much slower than actually reading it from someone else's memory. Okay. So, all IOs are slow, network access is fast, memory access is fast. So long as you have enough memory. Of course, you could say my data set is too big, I can't store it all in RDDs, then that is a valid point. Some of the RDDs will spill over to disk and slow down your computation. So, it is not a magic that everything is sped up, you will still limit it by how much RAM you have, but whatever you can use it effectively, it will speed up your computation. That is the basic idea. Okay. Any questions on this? Okay. So, this is basically Spark, and there are many concepts that I guess I did not cover, which is all of the transforms you can do, which is sort, group by, and so on. I am going to not actually go into those details here. The high level concept on Spark are store data in memory as much as possible, avoid disk IO, share memory across machines, okay, using a data structure called RDDs. Okay, that data structure is resilient to node failures because you can track how it was derived and only redo the computations you need to do. Okay. So, and then at the end of the day, it is still using MapReduce style frameworks where you can have parallel processing and you are feeding that data to the next stage and so on. No, that is it. I think I must have deleted a slide or two. So, we will stop here today, and